Good. So what we are going to do today is continue with our part 2 on MIMO. And what we finished with last week is we started talking about transmitter and receiver architecture for MIMO. So we still have a point-to-point system, multiple transmit, multiple receive antennas. But now we're going to dig a bit further into what kind of processing we can do the transmitter and the receiver. And the objective of this part is really primarily to look at the case where we don't know the channel state information of the transmitter. And the reason for this is that we already know what we can do if we know the channel. If we know that the transmitter and the receiver, we know what to do. We can do this SVD decomposition and then pre-code on the right side and combine on the left side, and everything go quite smoothly. So what we're going to look at here is more when we don't know the channel at the transmitter. We still know it at the receiver, but we don't know it at the transmitter. And so we're going to look at some transmitter architecture, so space-time encoder architecture, and then we're going to look at some receiver architecture. And the receiver architecture, you will see, even though we're going to focus here on the case where we don't know the channel at the transmitter, those receiver architecture can be also helpful in other scenarios, and you will actually play with this in coursework 3. Right, so we had this space-time encoder that we finished with last lecture, where essentially here we have B bits coming in. They are converted into Q symbols, and then we map those Q symbols into space and time using form of matrix, essentially, that is reflected here by this code word C. That is NT-dimensional, so NT rows and NT antennas and T symbol duration. Right, so one example of this is the Alamuti, where you take 2 symbols, so Q is equal to 2, and you map this into an Alamuti matrix that is a 2x2 matrix. Right, if you do something else, you could actually have, for instance, 4 symbols at the input and map this into a 2x2 matrix, where actually each symbol is mapped into a certain frequency, antenna and a certain time instance. Right. Now, those two would have very different performance, and we will see this later on today. Right. So the system model we're going to play with is the following one. Still no change compared to what we had before. We're going to have N transmit and N receive antennas. We're going to have a frequency flat fading channel. So that's the assumption we always had in this module. And now we have code work that spans T symbol duration. So the NT antennas spanning NT transmit antennas and T symbol duration. Right. And this is contained in a code book C. What does that mean? That means that actually here, if I look at this example of the Alamuti here, and if I have QPSK like this one here, each of those symbols C1 and C2, for instance, they could come from a QPSK constellation, right? So I can create many matrices like this every time with C1 and C2 coming from different symbols in that QPSK constellation, right? And so I can create a code book of matrices, of 2x2 matrices, where each matrix corresponds to a different pair of symbols, QPSK symbols, one for C1 and one for C2, for instance, right? Good. So at the K-time instance, I'm going to have a receive observation vector, dimensional NR. I have my channel matrix HK, and I have my columns of that code word C at time K. This is one of these column K of that code word C. And I have the noise at time K. So here we're going to assume noise is AWGN, as always. And we're going to look at the case where we don't know H at the transmitter, right? So we don't know H at the transmitter, so we cannot do this SVD. And we're going to look at, you can have different scenarios. You can have the scenarios where actually HK is is very slowly varying. So that means actually hk is actually a constant across that length t, right? So this, we could say this is a slow fading channel. So the current time of the channel is much longer than the duration of that code word t. And in that case, I can simply drop the index k, and I can say, okay, my channels is simply constant, right? I'm going to assume that channels is coming from distribution, and we're going to assume here is IID distributed, right? So this is the slow fading case. The fast fading case is when t is larger than the current times. That means actually this hk here can actually vary relatively quickly between different symbol instance, right? So in that case, you're going to have a fast fading. And so if your code word here is a length t, that means actually you're able to encode over multiple realization of hk, right? If t is larger than the current time. Good. So you can have those two scenarios. The one we're going to look at mainly is the slow fading one. But if you're interested, you can find the fast fading in the book, in the Meng book. Good. So let's look at that. So what are we going to assume at the receiver? So we have this going to be our transmitter essentially. Our code word C is this one here, right? Is the same as what we have here, right? And at the receiver, we have to define a certain architecture we can have. And so the first one we're going to look at is a receiver that is based on maximum likelihood criterion. And this is actually a very popular one, relatively complex, but is a very popular one. And the way it works is exactly the same as what we did for the SISO case. Remember, in the SISO case, we were looking at, if this is a scalar, we were looking at this, right? And you were trying to find the constellation point C, for instance, in QPSK, can have 4 points. And you were finding the C among those 4 points that minimize the square of the deviation between your receive observation and HC. And so for this, to do that, you need to know H at the receiver in order to do this operation, right? Now here in the MIMO case, the maximum likelihood is actually an extension of this. And so the way you obtain this is by starting from the PDF of a normal random variable, as we did quite several lectures ago. Now you can actually apply exactly the same principles to the multi-dimensional case, and what you're going to end up with is the following. You're looking at the among all possible code works that we have in this code book, you're looking at finding the one that minimize the sum over the t time instance, t's symbol instance, of the difference between your received observation vector at time k and your hk-ck, right? So it's always the same kind of idea. It's always a distance between your received observation vector and your hk-ck. And you sum over all those k because your duration here, your code word has a duration t, right? So if you look at the PDF of Gaussian vectors, essentially, you can actually figure out this expression relatively straightforwardly from this PDF, just by following exactly what we did here. Right. Now this assumes we have Gaussian noise, so the noise here has an identity matrix or scale identity matrix, right? So if you have something different than that, then this expression may be would be different. But here we assume we have a scale identity matrix. Right. So what does that mean concretely? It means that now you have a code word. You have. Let me give you an example. So let me do this with Alamuti, for instance, right? But it doesn't have to be Alamuti, because we know with Alamuti we can simplify the processing at the receiver so that we don't need to do this joint decoding. We can do a decoding for each symbol C1 and C2. But let's imagine we want to do a joint decoding. So I have Alamuti is something like this. I have let's imagine that I have a constellation here, and I have, let's say, points A1, A2, A3, and A4. And because I transmit two symbols, I'm going to have two constellations, right? So first symbol will be chosen from constellation A, the second one from B. B1, B2, B3, B4, right? So now, for instance, what I can transmit, one code word could be, for instance, my code word, one example of a code word. Let me give you multiple examples in this code book. So this code book that we had C, right? Same notation as what we had here, our code book C, is all possible matrices that I could transmit. So consider I could transmit A1 using Alamuti. So I want to transmit A1 from antenna 1, and let's say B2 from antenna 2. So I would do A1, B2. So remember, we have C1, C2, minus C2 conjugate, C1 conjugate. So C1 is now A1, and C2 is B2. So I'm going to have minus B2 conjugate and A1 conjugate, right? So this is one example, one possible matrix I can transmit. Then in that case, I transmit this symbol with this symbol, right? I could have A1 with B1. So I'm going to have A1, B1, minus B1 conjugate, A1 conjugate. This could be another matrix, right? I could have A1 and B3, A1, B3, minus B3 conjugate, A1 conjugate, right? I could have A2 and so on, right? So you're going to have many combinations like this, and this is your code book, right? So this is one example, one code word here, C, right, of inside this code book. And what I'm doing here, I'm finding, right, over all possible code words. Sorry, I say code book. This is code word, right? Over all possible code word in that code book, I will find the one that will minimize this, right? So I will go over all possible combination here. So if I have 4 here and 4 there, I could have 16 matrices, and I will go over all possible 16 matrices to find the one that actually is the one that minimize this difference. Okay. Now you see that actually here you have 16 matrices because you have the matrix for the first symbol and the matrix for the second symbol, right? If I had the other example here that I gave you, this one, I have now 4 symbols to transmit, right? Let's imagine that I want to build that code word. Now I have 4 constellations. I'm going to have to create A, B. Let me call this, not using C because we have it here, but let's imagine we have then D1, D2, D3, and D4, and then we have E, E1, E2, E3, and E4, right? And now I'm going to have matrices that following this argument here, right? I have 4 possible symbols coming from 4 different constellations. So I could have many different solutions here. I could have A1, and I have B1, for instance, and then D1, and then E1, right? Or I could have A2 and still B1, D1, and E1, right? Those are different code words, and so on. So in this case, my code words, my code book is much bigger. I have 4 points, and I have 4 constellations. So now I'm going to have 4 by 4 by 4 by 4, right? I'm going to have to look at a code book of this dimension, right, in order to find the best code words into that code book and do this. So you see that those are 2 different code books. This one based on Alamuti, this one where actually I have a higher multiplexing rate because I map more symbols into 2 by 2 matrices. But here I have to do a much higher, much more intensive search because I have many more combinations, right? Now I will come back to this later on, but you remember with Alamuti, I mentioned this earlier on. I said if your channel is not frequency flat, is not constant over 2 time instant, then you have to do this joint decoding. But if your channel is constant of the 2 times symbols, then you can do the simple match filtering at the receiver, and you would decouple those two symbols C1 and C2, right? So in that case, you don't need to do this full ML decoder. What you can do is that you can simply do the match filtering at the receiver, and then do a SISO maximum likelihood decoder for the symbol C1 and one for the symbol C2. And in that case, you would look at a maximum likelihood decoder for the constellation A and for the constellation B. You're going to have only 4 search here and 4 choices here and four choices there, right? So this is the case where you actually use Alamuti, and you have perfectly constant channels over 2 channel realization over 2 consecutive time instants, right? But the general case is this one, and has higher complexity. So we'll come back to it later on when we go into Alamuti again. Right, so the question I want to ask here is that given that we have a certain code book, right, that is made of many code words, what I want to look at is at the receiver side, what is the probability that the receiver, this ML decoder, will decode another code word instead of the intended one, right? So imagine you transmit a code word C, but the receiver decodes the code word E, right? So for instance, you transmit a code word C, this one here, we change color. Imagine this is C, this is what you transmit, right? But what you're interested in is to understand what's the probability that the receiver will confuse C with, for instance, E, this one, or C with this one, right? So what's the probability that actually you decode with a wrong code word? Right. That's the same idea as what we do in, and what you did already in your first course on communication, when you look at QPSK, and we're looking, for instance, what's the probability that I confuse this symbol here with this one, right? Or this symbol with this one, or this one with symbol, right? And this is what we did in part 1, very quickly, right? We looked at the distance between those points, right? And then we were averaging after over the distribution of the channel. Right? So here is the same idea, but instead of looking at one point, right, here we're looking at the probability of confusing one code word with another code word. So instead of being just one symbol, is actually a matrix. What's the probability of confusing a matrix with another matrix, right? And that matrix already contains multiple symbols that are packed into space and time dimension. Right, so this is called pairwise error probability. That is the probability that we confuse C with E, and this is denoted like this, for given realization of this channel, right? So we know this channel for given realization. And what is this error probability? Well, it's something very similar to what we had earlier on in the modules when we had the SISO case, is essentially our long-term SNR multiplied by a quantity here. You have more details of this in the lecture, in the book. But essentially this, if you like, is the same as what we had earlier on, where we were talking about H multiplied by D, by a distance, or D min, right? I had the minimum distance. This could be my minimum distance here between these points and these points, right? And we had something like this, H squared. Now, I have something a bit more complicated here, but you see, this is like my D min, is my difference between a certain code word, the column of a certain code word C, and the column of another code word E. If I particularize this to the SISO case, in the SISO case, what do I have? I have HK becomes H, right? Simply, I have a scalar, and I have only one time instant, and I have CK minus EK. CK is just a scalar, and this is a scalar, complex scalar. CK minus EK would be the distance between maybe, for instance, this point here and this point here. So that's going to be that distance, right? So in general, I don't have necessarily the minimum distance. I just have a distance and then the distance squared. So where D would be C minus E squared, right? This is what we had in the SISO case. Now I have something slightly more difficult here, because I am actually dealing with vectors. Right. What I want to show you here, I will not go into all the math, but I want to give you some insight into what you get at the end and how you can design good codes for this. All right, so remember what we did in the SISO ISO case, we had this error probability for a given realization of the channels, and then we were saying, okay, now I have to average over all realization of the channels. And for this, we were saying we have, for instance, relay fading, right? This is what we did, and we had the average error probability. Here we can do exactly the same thing. So I have my pairwise error probability for a given realization of HK, and now I can find my average pairwise error probability when I'm averaging this conditional one over all distribution of the channels, right? So this is condition on this specific realization of H. And if you average over all realization of H, now you have your average pairwise error probability. And so what we're going to do next is say, well, simplify the system a little bit. Let's look at high SNR and try to find what actually the code words, the pairs of code words C and E that leads to the worst pairwise error probability, right? So in the same case as here, we had, in the CISO case, we had different points, right, with different distances, right? And we were saying this error probability at the end is mainly dominated by the points that have a minimum distance. So this point C will likely be confused with this point here and this one because they're closer to C than point E, right? So this is what we had when we were talking about the minimum distance. And here is a bit the same idea. We're going to calculate an average pairwise error probability and then try to find actually which pairs of C and E leads to the worst case, right? So if you like the minimum distance. Good. So once you have that, once you have this pairwise error probability, right, you can calculate a diversity gain and a coding gain. And what we'll see is that this pairwise error probability for a given code word C and E will be written as something like this, where we're going to have an argument here, GC, that will multiply the long-term SNR row and will actually be information about the coding gain. So actually with the structure of the code that will try to increase the SNR. So the effect of GC here, you see, will be to actually increase the value of rho, so increase the SNR. So if you have a slope like this as a function of the SNR, if you have the GC is increased, essentially it means that the slope does not change, but you're shifting to the left, right? And we're going to look at this argument here of GD, which is the argument, the exponent of rho, which will be the diversity gain, right? And diversity gain will be the slope here of that curve of that pairwise error probability as a function of the SNR. And what we will try to find is what are the pairs of C and E, right? In this code book, what are the pairs of C and E, right? For instance, this is E. I confuse C with a code word E. What are the pairs of C and E that will lead to the worst performance? Because the worst, those pairs actually will be the one that will dictate the performance will primarily dictate the performance of the system. Right? And so we'll find from there we'll be able to identify what kind of code book of code word is better. Right? Okay, good. So how we do that? Quickly, you can do this for more complicated stuff, but the main idea is actually following it. The expression looks a bit more complicated, but the philosophy is exactly what we did earlier on. You start with this conditional pairwise error probability. So it's conditioned on a certain realization of the channel. And then you say, well, I don't like this Q function because a Q function is, we cannot manipulate this easily, right? So what you say is that, okay, let's use an upper bound on this, and let's use this Chernoff bound, this. We have done this before. So instead of having a Q of this big expression here, I now replace this Q of X by exponential. So this means I'm going to have exponential of minus x squared. So I'm going to have here minus rho over 4 of this quantity, sum, hk, ck minus ek. That's what we're going to have. Right. I'm just writing this argument here. Right. And now what do we do next? We say, no, I need to do an average. We need to compute the average over the over all realization of H. So I'm taking an expectation over H, right? So we end up doing what? We end up to do the following. We have essentially to take an expectation over HK of this quantity, right? So what does that look like? That looks something very ugly, but actually this is nothing else than the moment generating function. This is nothing else than saying expectation of E T multiplied by a random variable, right? So my random variable is actually a function of this quantity here, right? Is a function of H, so it's a random variable. And I'm going to have an evaluation at a certain point T that will give me essentially my my probability of error, right? So now finding this moment generating function that depends a lot on the structure of this guy here, right? So you will see in the book you have this for different distribution of H. If you have slow fading, if you have fast fading. So if you have slow fading, you can replace H of k here. If you slow fading, H of k becomes simply H is constant over all the code, across the code words. Right. If you have correlation the time between H at time 1, H at time 2, H at time 3, you can take into account this. If you have correlation between antennas, the entries of this channel H, you can take this into account. You get just more complicated moment generating functions. If you have something else than Rayleigh fading, but you have something that like Rishon fading with the presence of line of sight, you can do this as well. It just makes it complicated. But the philosophy is always the same. You start with your pairwise error probability, conditional pairwise error probability, so conditional realization of H. You upper bound this using the Chernoff bound, and then you compute a moment generating function. Right, so let's do that here for slow fading. So I have a slow fading channel, so now I'm assuming my HK are actually the same for all K is equal to H. And H now is, I will assume it's IID distributed. So H is, I'll denote this like omega here, is white, so this is IID distributed. So the entries here are circularly symmetric complex Gaussian random variable. They're all independent from each other. Right? And so by taking this Chernoff bound and this moment generating function, what we end up with is something that is much simpler. And we end up with this. Okay, so what is that? Now we have a determinant of an identity matrix, SNR, and then we have here an error matrix. The error matrix is simply C minus E multiplied by its Hermitian. Okay, now you see the determinant of I plus something here. This is quite similar to what we had in the MIME already before. Remember, we had this determinant of identity matrix plus H multiplied by H Hermitian, right? And we did this a few times already. We did the SVD of that, and we could actually express this actually as a product of 1 plus eigenvalues, right? Here is exactly the same thing, right? So how we do that again is right. So if you have the determinant I of NT, let me give you an example right away, so it will be maybe easier. Right? Imagine I have NT. Let me take NT is equal to 2, and I have T is equal to 2. So like this Alamuti example, right? Or the 2 by 2 matrix we had before. So here I have I2 plus rho over 4 of C minus E multiplied by C minus E Hermitian, right? So this is a 2 by 2 matrix, right? So my C minus E Hermitian, I can take it as VD of this V lambda is right, is Hermitian, so I can take an eigenvalue, not SVD, eigenvalue decomposition. And here for the gamma, I'm going to have two entries, lambda 1 and lambda 2. Right. So That's, I write this determinant of I2 plus rho over 4 v lambda v, right? And we have done this before. This is determinant of I2 plus rho over 4 vh v lambda. This is identity matrix. So I have determinant of I2 plus rho over 4 big lambda. Right, so this here, I have 1 plus rho over 4 lambda 1, 0, 0, 1 plus rho over 4 lambda 2. And I take a determinant of this, that's the product of the diagonal entries. So I'm going to have 1 plus rho over 4 lambda 1, 1 plus rho over 4 lambda 2. Okay, so this is exactly what we have here. Now you have the minus nr here. Right, so imagine you have two receive antennas, so you're going to have here minus 2, and so here you're going to have a minus 2. Okay, so this is what it means. Now what you see here, I have two eigenvalues, right? I have two eigenvalues of this error matrix E tilde, right? I have at most two eigenvalues, two non-zero eigenvalues, right? So if one of those two is equal to 0, then one of those terms disappears, right? Now let's imagine I'm looking here at high SNR. So at high SNR, what will happen? If rho 1 is strictly larger than 0 and rho 2 is strictly larger than 0. So in other words, that means actually here, the rank of this is equal to 2, right? I have two non-zero eigenvalues, so that means that the rank of this is equal to 2, because this is a 2 by 2 matrix, so the rank is at most equal to 2. Then at high SNR, if rho is very large, I'm going to have something roughly y1 multiplied by y2 multiplied by rho multiplied by rho, that rho square, and I have, so rho to the power minus 2, rho to the power minus 2, I have rho to the power minus 4, and here I'm going to have rho power minus 2. Right? This is what it means. Right? What that means is that if I have two eigenvalues that are non-zero here, I'm going to have now here a diversity gain. The exponent here is equal to 4. Right? I have two transmit antennas, I have two receive antennas, and I get a diversity gain equal to 4. Right? But to have this, I need to have those two eigenvalues, lambda 1 and lambda 2, to be non-zero. If I have one of those two is 0, if I imagine that lambda 2, if lambda 1 is larger than 0 and lambda 2 is equal to 0, at high SNR, I'm going to have simply rho here to the power minus 2, right? And lambda 1 minus 2, right? So I'm going to lose here in terms of diversity gain. I'm going to have a diversity gain only of 2, not 4. Only 2. Right. Now, what do you see from this? What is important is the rank of this matrix here. So here, if you have this here, that means that the rank of this error matrix is equal to 1 instead of being equal to 2. Here is equal to 2, here is equal to 1. Right. So this is what you see here, is that if you have your lambda here, in general non-zero, in general it could be 0. What matters is the product here is from 1 all the way to the rank of this error matrix, right? So in this example here, if I had only one of them, the rank is equal to 1, so I have only one non-zero eigenvalues, and so I'm going to have here the rank is equal to 1, I have only one term. So at high SNR, what we end up with is exactly what I wrote before, but for the example, we have this. We have here the exponent of the SNR is NR, because I have NR receive antenna, multiplied by the rank of this error matrix. And then I have a term here that is a function of the eigenvalues of this error matrix. Right? And so what you want to do, you want to make sure that this exponent here is as large as possible, and that this term here is also the product of the eigenvalues, essentially, this one here, is also as large as possible. So if you maximize the rank here, it means that if you have a rank in the example here, if I have a rank of 2, let me change color or page. Right, so if I continue here, if I have those two examples, right? So if I look at this as a function of the SNR row, right? So if I have this case here, I have a rank of 2, so I have a diversity gain of 4. That means I'm going to have something that goes like this. Diversity gain of 4 for a rank equal to 2. This one, I have a diversity gain of 2, right? Because the rank of my error matrix is equal to 1, right? So you want to make sure that, you see, if you have two different code words C and E that are different from each other, obviously they have to be different, otherwise there is never error. But if you have two different code words, if C and E are such that the rank of this matrix is equal to 2, that means actually the probability of confusing C with E will actually decay quite quickly with the SNR, right? But if the rank of that error matrix is equal to 1, well, the probability of confusing C with E on average will not decay that quickly with that SNR, right? And so you can imagine this is a probability of confusing from C with a certain code word E1, and this is probably C with code word E2. So if you have in your code book, you have multiple code words. You have your code word C, for instance, you have E1, E2, and all other code words in your code book. You're going to have to look at all possible pairs, right? C with E1, C with E2, E1 with E2, and so on. All possible pairs, and find the one that actually gives you the worst performance. And what are those? Any pairs here between any two code words that are such that the rank of the corresponding error matrix is very small. Because if this happens, that means actually this kind of events will lead to a pairwise error probability that will be quite large, that will not decay fast with the SNR, right? And so this is the basics of this determinant, rank-determinant criteria, and it says the following. It says that if you have an IID relay fading channels, slow fading channels, what you need to do, you need to maximize the rank. So you need to look at overall, you look at the error matrix over all possible pairs of code words that you have in your code book, so that C and E are different from each other, and you look at the minimum rank among all of them, right? So in this code word, you look at C with E, and then you say rank of C minus E1 multiply C minus E1 permission here is equal to, for instance, in this case here, the rank was equal to 2. Then you say the rank of C minus E1 minus E2, we look at the other one, right? And in this example here is equal to 1. And then you look at the rank of all the other pairs, right? And so what you do here, you find the minimum rank over all those code words. So among all those possible pairs of code words, you look at the minimum rank. So let's imagine it's this one, right? So your minimum rank is equal to 1. So the performance of that code book C here will be driven by this minimum rank equal to 1 only. If you have another code book, let's say I have another code book star, where I have another set of matrices, right? And I find that actually, let me call those matrices A, B, and so on. And if I write the rank of this error matrix here is equal to 2 all the time, whatever options of A and B I found, any pairs of matrices here, I always find 2. That means actually even the worst case rank, the minimum rank here will be 2, will be larger than the minimum rank I have there. That means actually my worst performance, my worst pairwise error probability will be better off with this code book than with this code book, right? Then you better choose that code book. You better choose that code. Okay, so this is what this says here. Your rank criteria is among all possible, code books, all possible codes. You try to find the one that maximizes the minimum rank. And so if you have matrices E like this, right? what is the maximum rank you can have? Rank of E tilde here, the rank of this, is at most equal to the minimum between, is at most, the minimum between T and NT, right? If you have C minus E is just T is equal to 1 and then T is equal to 2, the rank of this would be equal to 1. Right? So the rank of this error matrix is at most equal to that. So in the example I gave here, if T is equal to 2 and NT is equal to 2, the rank is at most equal to 2, right? So the maximum rank you can expect is equal to 2 for this error matrix. So you should try to aim to have this maximum rank, which is 2 in this example, right? Good, so this is what it means here. If your minimum rank is equal to NT, so it's always, I said, minimum between NT and T. But if T is larger or equal to NT, there is a chance that your minimum rank is equal to NT, right? And in that case, things are quite nice, because essentially it means that you can get the maximum possible diversity gain you can expect from this MIMO transmission. Now, once you have done that, once you have maximized the rank, then what you do after, you maximize the determinant. So if you have multiple code book like this one and this one. So between those two, we know that actually this one is already better because the minimum rank here is larger than there. Right? But you could have another scenarios where now I have a third code book, 2 tildes, where I have again other matrices, Y, Z, W, and so on. Right? And those are again 2 by 2 matrices, right? But different set of matrices than what we have here. And I find that the minimum rank here, the minimum rank over all possible error matrices is equal to 2 as well. That means that those 2 code book will achieve the same diversity gain. They will achieve the same diversity gain because the worst pairwise error probability will scale in the same way. The slope will be the same for those 2. So how do I choose between those 2? Well, I look at the second part of this equation here, which is this one. Let's say this one, I want to minimize this. So to minimize that, I need to maximize that quantity. So this is the coding gain. This is the coding gain. So if you have 2 code books that have the same rank, minimum rank, you can look at the coding gain to see which one is the best, right? And so what that means is that if they have the same rank, it means that we're going to have the same slope, right? But if one has a larger coding gain than the other one, that means actually one will be better than the other one because it will be the performance, the error probability will be shifted to the left. That's what it means. Okay, so this is called the rank-determinant criteria, very famous in MIMO. That was invented in 1998, 99. And that actually created the whole design of MIMO codes. Right, so this is the way it works. And so you can apply this to any code. So one more thing here. So if you have this, if the rank is equal to the number of transmit antennas, then maximizing this, that means that the rank of this is equal to NT. You end up with actually a matrix that actually an error matrix that is full rank. The product of the eigenvalues of a full rank matrix is equal to the determinant, right? So that means actually E tilde, right? E tilde is C minus E permission. This is a NT by NT matrix, right? If we say that the rank of this matrix is equal to NT, it means actually we have a full rank matrix. So the determinant of that determinant of E, if it's full rank, is equal to the product of the eigenvalues of E tilde, 1 to NT. Okay, so in that case, it's called the determinant criteria, because if you have a full rank error matrices, then what you do is that you distinguish between 2 code books using the determinant, right? So if your 2 code books have the same minimum rank, and their full rank is equal to the number of transmit antenna, then you just compare the determinant between those two. And the one with the smallest determinant is the one that actually will have the lowest performance. So you try to maximize the determinant among those of a given code book. Okay, so let me give you an example so that you understand how it works. So let's go back. Let's take 2 nt equal to 2. And I give you 2 examples. The first one, which is a full rank code, is called also full diversity. Full diversity, you understand why? Because if it's full rank here, if the minimum rank is equal to nt, right? You know from here, right? If the minimum rank is equal to nt, that means actually that the rank of the error matrix will be equal to nt. So we're going to have nr by nt. So that's the maximum diversity gain I can get. Remember from the diversity multiplexing trade-off, the maximum diversity gain we could have is nr by nt, right? So if you can have a full rank code, you get full diversity gain. Right, so a full diversity gain, you're going to need the minimum rank is equal to nt. If you have a rank deficient code, the minimum rank is smaller than nt. Right, let's look at an example of 2 of this, a rank deficient and a full rank code. So I have the same, I have 2 symbols, C1 and C2, that I want to transmit, 2 transmit antennas. Right. The first one, I simply transmit C1 and C2 on those 2 antennas over 1 symbol duration. So here I have T1, T is equal to 1. The other one here, I have 2 symbol duration, and I do C1, C2 minus C2 conjugate, C1 conjugate. So I have T is equal to 2. Right? Now my code word here will be look like this. Right? My code word here will look like that. And so now the probability, what's the probability I confuse C with E with another code word? Well, another code word for this kind of code is this. Another code word for this kind of code is for Lamuti is this, where C1 and E1 are just probably 2 different symbols in the constellations, right? So I have a constellation for the first one, right? And I have 2 different symbols here, and I have a constellation for the second stream here, and I have 2 different symbols there. And C and E are different from each other. So at least the C minus E should be different from 0. So at least the first entry or the second entry should be non-zero. Right, so this is a rank deficient code, obviously. Why? Because T is equal to 1, right? So the rank of E tilde here is at most the minimum between 2 and 1, right? Okay, so what is this? Is in this case is 1. So I have rank is equal to 1. So here I cannot expect, if I have 2 receive antenna, I can expect to have a diversity gain of 2 only, right? And R multiplied by the rank of E. And R is equal to 2, for instance, and the rank of E is equal to 1. I'm going to have only a diversity gain of 2, right? Good. Other example, the Alamuti. If I do Alamuti, C minus E, and I multiply by its Hermitian, that's the magic of Alamuti, I end up with something like this, right? And so here, this rank, the rank of, this is E tilde, the rank of E tilde here is equal to 2, always equal to 2, as long as C is different than E. If C is different than E, this is non-zero and this is non-zero. So this matrix will have a rank 2. Because of that, I will have a diversity gain of 4 if I have 2 receive antennas. Right? So here I'm going to have a diversity gain of 2 if I have 2 receive antennas. Here I'm going to have a diversity gain of 4 if I have 2 receive antennas. Right? I multiply by a factor of 2 the diversity gain, because here I have a rank that is equal to 1, while here I have a rank that is equal to 2. So that means actually I have higher diversity gain with this full rank code than this rank deficient code. Now, on the other hand, you can argue, yes, but here I use only 1 symbol duration, right? So indeed, so my multiplexing rate here is actually higher than here, because here every symbol duration I transmit, every 2 symbol duration I transmit only 2 symbols, while here at every symbol duration I transmit 2 symbols. So my rate here is potentially twice as high as there, right? So this full rank code here will have a higher diversity gain, but if you want to have the same spectral efficiency, you will need to use constellation size here that are much higher than here. For instance, if I use QPSK here and QPSK there, so I use 2 bits per second per hertz here and 2 bits per second per hertz there. That's 4 bits per second per hertz, right? If I do QPSK here in the Alamuti one, I'm going to have QPSK here, QPSK there, but I repeat them again. So my spectral efficiency will be only 2 bits per second per hertz if I do QPSK. So to have the same spectral efficiency as here, I need to increase the constellation size, and I need to have 16 QAM. So if I use a 16 QAM for C1, a 16 QAM for C2, I have 4 bits per second per hertz for C1, 4 bits per second per hertz for C2. I'm going to have then 4 bits per second per hertz totally for this Alamuti code, right? Then I'm going to have the same as there, right? So you could say, well, my Alamuti will use 16 QAM, will have a diversity gain that is 4. In contrast with this rank deficient code that will use only QPSK and will have a diversity gain of 2, right? So there is pros and cons here, because there you have only QPSK, so the distance between the points is actually larger than if you use a 16 QAM, right? That's good, but on the other hand, you have only a diversity gain of 2, so your slope will be lower, right? So there is the trade-off. So if you grow to larger and larger dimension of your MIMO system, it's become complicated to see whether you would need to have, you know, smaller constellation with larger distance between the points, but there could be rank deficient, or actually codes that are full rank, but then because of maybe this the fact that you replicate, you actually end up with a loss in the spectral efficiency that leads to actually you need to use larger constellation size. So I will show you simulation results later on that compare those two kind of codes. Okay, but if you can, the best you can do is try to find a full rank code that at the same time has a large multiplexing rate, so that packs as many symbols as possible. Full rank and large minimum determinants. Right. So here's another example, and you can do this as part of your homework. So here is you have 4 symbols now, right? So here I had 2 symbols for each time instance. Here I had 2 symbols for 2 symbol duration. Now I have 4 symbols that I packed into 2. T is equal to 2, but now I have Q, I pack 4 symbols, right? So I pack twice as many symbols here than here, right? I pack the same number of symbols here than there, right? For each symbol duration, I had 2 symbols. Here, for each symbol duration, I had on average 2 symbols, right? Now you can say, okay, so now I have a 2 by 2 matrix here, and here I have a 2 by 2 matrix. But still, I transmit twice as many symbols here than there, right? But do I still have the advantage of here that I have a multiplexing gain of 4? Sorry, a diversity gain of 4, right? If I have 2 receive antennas. Well, you have to look at the rank of this. The rank of this error matrix, you look at C minus E, and then you check for all possible constellation points what actually the rank of this would be equal to 2. And it turns out that this specific code here, the rank is equal to 1. So in other words, yes, you can pack more symbols, same as what you have in this example here. You pack many symbols, so you have Q over T is equal to 2, which is twice as large as what you had here. But you still have a rank that is equal to 1 only, instead of being equal to 2. Right? Now you can be smarter than that. You can design codes that are such that you can indeed have a rank here that is actually equal to 2. And that still packed 4 symbols that exist as well. It just makes it more complicated because the maximum likelihood decoder, what we'll have to do, it would have to find all possible, across all possible, code words in the code book, find the best one. And that means that if you use QPSK, you're going to have 4 choices for C1, 4 choices for C2, 4 choices for C3, 4 choices for C4. So if you have an M quam constellation, you're going to have M for the first one, M for the second, M for the third, M for the fourth, so M to the fourth, right? So if you have 64 quam, 256 quam, and you take to the power 4, suddenly you have large number of combinations to look after, right? And then that's only here for 2 antennas. Now imagine now if you want to have 10 antennas, and you pack many symbols into those matrices, then the maximum likelihood decoder, the number of combination explodes and increase exponentially with the constellation size and potentially the number of antennas as well. Right, so this can be an issue. So we need simpler receiver in that case. Right, okay. Any questions here? Let me have a break of 5 minutes, but feel free to ask me any questions, right? If anything isn't clear, let me know. Okay, so let's resume at, yeah, in 5 minutes roughly. Okay, any questions? Okay, so if not, let's continue. Right, so what we're going to do now is to look at specific class of code here. So actually what I did here, this argument here, this rank-determinant criteria holds for slow fading channels. It holds for any types of codes. So as long as you can have a code that is characterized by a code book of code words, you can always use that. Now, to construct the code, you can have specific techniques and specific framework, and one of them is called specific space-time block codes. And the particular case of them is the linear space-time block code, which actually the most common one. So space-time block codes is one case where you map those Q symbols onto the code work NT by T, as we have seen before. But that might not be the only way of doing that. There are codes actually that perform, error correction coding as part of the space-time codes. In those ones here, the space-time block codes, there is no error correction that is occurring as part of this STBC. The error correction is done before, where you map the bits to the symbols. In that operation, you do error correction first, and then you map them to the space-time code. Now, the linear one is the most used, and they spread the symbols in space and time using some form of linear relationship. And so using simply, essentially, you have the energy of one symbol will be multiplied by a matrix. And so you can view a linear space-time block code simply by using a linear relationship to map the energy of a symbols to a given to space and time. And so one example of this is the one we have used already now. All the examples I gave you, this one, this one are all examples of actually linear space-time block codes. And the reason for that is that you can write this one here, for instance. How can you write this? For instance, you can write this as follows. Right, if you have C is 1/2, C1, C2, right, for instance, you can write this as 1/2, 1, 0, C1, plus 1/2, 0, 1, C2, right? And you can do this for other codes as well, right? For the Alamuti, you cannot do exactly with C1, but you can do something with the real part of C1 and the imaginary part of C1, right? So what you see is actually you have kind of basis matrices here, and those basis matrices will multiply the symbols. And the question is, when you design the linear space-time block code, is how you design those basis matrices that will multiply all those symbols, right? So this is the structure of a linear space-time block code. Those are the most popular one. And I have to say that in practice, the two that I used, if you take a system like 4G, 5G, the two that are really used, actually the two I just mentioned already now, this one and this one. So this is the Alamuti. This is called spatial multiplexing. So the rank deficient there is called spatial multiplexing. It's actually what it means. You transmit two independent streams, C1 and C2, onto two different antennas. That's it. Right. Those are the simplest case, and actually those the commonly used one. Things that are more complicated like this, where you start mapping multiple symbols into multiple time duration, this is actually not used because it makes the system more complicated and the performance gain is not that significant. Right, so what we're going to look at is essentially those two cases, the spatial multiplexing and the Alamuti. The Alamuti we know already what it is, so I will not go over it again, but I will show you examples of how does Alamuti works when you have 3 antennas, 4 antennas. Is there something equivalent to Alamuti? But before doing that, I will go into maybe the most popular one, which is simply the spatial multiplexing. So the spatial multiplexing, and this is called also V-blast and sometimes D-blast. There are some differences, but this is actually a full rate code. So the number of symbols you transmit per symbol duration is equal to the number of transmit antennas. And so it really tried to favor, if I go back to the definition, we had a multiplexing rate at the beginning here. Our spatial multiplexing schemes here, if you remember this, the spatial multiplexing rate, if Q is equal to NT, and T is equal to 1, you have this ratio is equal to NT, essentially. So you try to really transmit as many symbols as possible, right? This is really the spatial multiplexing scheme that we have now I will describe is really going along that direction, right? The Alamuti schemes and other form of space-time block codes that I will explain later on do not have a spatial multiplexing rate that is as high, but will have a higher diversity gain. Good. So what is the structure of the spatial multiplexing schemes? Is exactly what we had here. So here we actually transmitted 2 streams across 2 antennas. Now if you have NT transmit antennas, guess what? You transmit NT symbols. Right? So this is for each symbol duration, essentially transmit NT independent symbols. Now obviously what that means concretely is that if you have NT antennas for 1 to NT, what it means actually you lose every time you lose independent streams. So you have bits of information 0, 1, 0, 0 that's coming. You encode this using a strong error correcting code, turbo code, polar code, LDPC, conversion code, whatever code your favorite code, and then you get a sequence of symbol C1, C2, C3, C4 that are mapped, right? And then what you do at each symbol instance, you transmit C1, C2, C3, C4, and so on from that antenna. So that means that your symbols C1, C2, C3, and C4, they're really coming from your bit streams from that antenna. They are not encoded across different antennas. They just go through one antenna, right? Same here. I have symbols, a sequence of bits that are coming in. I encode using my favorite error correcting code, and I have another sequence of symbols. I don't know. Let me call this. Sorry, C1 and C and T are not the same as here, right? This is actually. Let me use another notation, otherwise you will get really confused. So let me say, okay, my symbols here are A1, A2, all the way to I don't know, whatever number, right? So this is a symbol. This is another symbol. And then you have the second stream is B1, B2, and so on. That's the second antenna, right? And so if you look at one symbol duration, this one, right? For instance, I'm going to have C1 will actually be A1, C2 will be B1, C3 will be this one, C and T will be this one, right? Because there is no encoding across time. This C1 is not repeated across time at other antennas. You can simply look at this at each symbol duration. Okay, which is quite different from the Alamuti, because here you have this symbol is actually now repeated at the next time instance, right? So over the other antenna. So you see that the symbols now is encoded across space, right? The same information, the same symbols is repeated, but on the other antennas. Here, not at all. You don't care. You transmit C1 on antenna 1, and you don't repeat it on any other antennas. Okay, so what can you say from this? You have now a symbol C, you're going to have a symbol E, right? Another element in your code word that will be E1 all the way to E and T, right? C is different than E, right? So your error probability will be a function of C minus E remission, right? What is the rank here of E tilde of this error matrix, well, the rank will be equal to 1 because essentially this has a rank of 1. T is equal to 1, right? So what I can already say here with this, if I transmit independent streams over those different antennas, the maximum diversity gain I will get from this will be equal to the number of receive antennas at most, right? Because the rank here of E tilde is equal to 1. So if I go back to this, if I have a slow fading channel, does not matter. You know what I have, the rank is equal to 1, so my diversity gain will be equal to NR, the number of receive antennas. Good, and so this is what you see here. What I have here is nothing else than the expression I had earlier on. So let me write this. You understand where that comes from. So let me go back to this. That's the advantage of teaching in class face-to-face, that you have a big whiteboards, and so you can see, you don't have to switch from one slide to another one. Let's use that, right? I have determinant of that. Okay, so what is that? I have determinant of I and T plus rho over 4 E tilde, and I have minus NR. Okay, so let's write this down. So I have determinant of I and T plus rho over 4, and I have C minus E permission minus NR. This is an NT by 1 vector, right? It's NT by 1 vector, right? This is NT by 1 vector. So C minus E is an NT by 1 vector. So this is equal to the determinant of, I switch the order, this one goes here. If I do that, I have to change the order of this. So if I switch the order of those two matrices, I will not have NT by 1 multiplied by 1 by NT. I will have 1 by NT multiplied by NT by 1. So I'm going to have C minus E remission, C minus E, NT by 1, 1 by NT, rho over 4, plus I'm going to have a 1 there, minus NR. What is the determinant of one scalar? It's just that scalar, right? Is 1 plus rho over 4. And here I have C minus E remission, C minus E remission multiplied by C minus E. So this is C minus E norm squared multiplied to the power minus NR. Okay. And now if I look at high SNR, if rho is large, I'm going to have rho over 4 minus NR C minus E square minus 2NR. Okay, so this is my pairized error probability of that spatial multiplexing scheme, assuming I do what at the receiver, assuming I do maximum likelihood, right? As long as I use this, once I start using this expression, I assume I'm doing joint decoding, joint maximum likelihood decoding of all the streams, right? And what I have is that. So this is what I have here. Sorry, I missed the NT somewhere. Yes, so the NT comes from here, right? So the C here, C minus 2, C minus E, if you replace C minus E by this, you're going to have the NT will appear. That will give you the NT there. You're going to have the sum. Okay? So what you see here is that what is my diversity gain is NR, right? That's not great, right? I could have NR NT, but I don't have the NT there because my symbol C1 is transmitted from antenna 1 only, is not, you know, this information is not transmitted from the other antenna. So there is no way I could get a diversity gain from the transmit antenna array. Right. Is that still good? Well, actually, it's good. If you have fast fading channels, so if you actually have the channel that changes quite quickly, this is typically performs over slow fading, but you can show that still this is useful if you have fast fading channels and you can have this bit streams here is encoded and encoded over a channel that is changing, it's actually sufficient to transmit NT independent streams here and to achieve the capacity of this system. And so this relates to what we had earlier on when we looked at the ergodic capacity of the MIMO channels, right, over fast fading channels. You remember we had an identity matrix. So we were saying if I have an IID channel, actually my covariance matrix will be actually identity. Well, what that means is that you transmit NT independent streams here. And what you do at the receiver, you do joint decoding. So if I go back and I look at what we were doing here over fast fading channel, right, this one here, I have input covariance matrix that is identity divided by NT. This is the same as what we just did before. Remember, I had this C is C1, C2, all the way to CNT, and now divided by 1 over square root of NT. That's the same. Those one, the covariance matrix of this will be actually an identity matrix because they're all independent from each other. And I have NT here because actually I uniformly allocate power across all the antennas, right? So actually what we can show is that this spatial multiplexing scheme, if you transmit independent stream from each and you do joint maximum likelihood decoding at the receiver, will actually achieve this capacity over fast fading channel, right? Over slow fading channels will not achieve the capacity simply because you don't even get the diversity gain, the full diversity gain. So if you look at slow fading channels and you have this diversity multiplexing trade-off here that we mentioned here, well, what is the maximum multiplexing gain I could have is maybe this, but what is the maximum diversity gain I get is NR, is 0 NR, right? We just computed NR, diversity gain. So that's going to be roughly the diversity multiplexing trade-off I would achieve over slow fading channels with this spatial multiplexing gain, right? So I will favor this part, but definitely I will be very low on the diversity gain, right? Good. So what is the drawback of this? Well, you see, if you start increasing the number of streams and the constellation size, things get quite complicated here, right? Because at your receiver, you're going to have, if you have M-QAM, right, and you have NT antennas, you have M to the power NT constellation point to search. And that can grow very, very, very quickly, right? So, so this is the reason why other receivers are used. So that's the maximum likelihood, but we can do something else. Very popular one, zero forcing. Right, so what can we do here? I transmit my symbols, so let me write my system model here again. Right, I have y is equal to this h multiplied by a vector c plus some noise, right? And so what is my vector c now is 1 divided by nt, c1, c2, all the way to cnt. Square root, right? So I can write this slightly differently. This is y is ds over nt, h multiplied by c1, c2, all the way to cnt, plus n. Good. Let's take a system where I have the number of receive antenna is larger than the number of transmit antennas. So let's imagine I have nr is larger or equal to nt, right? And let's take a very simple scenario. Let's imagine I have y1, y2. I have 2 receive antennas. And I have ES and T. And I have H, C1, C2. Plus N1, N2. Right. What can we do at the receiver in order not to do the joint maximum likelihood decoding. So if I do the joint, I'm going to have to do y1 minus h, I'm going to have y1, y2, h, c1, c2, right? And I take this, and I have to do the arg min over all possible c1 and c2, right? So my complexity will scale as m squared, right? What I want here is to have a complexity that scales linearly with m. So I'm going to have complexity m for c1 and m from c2. So I just want to apply a combiner here so that I can simply decouple those two streams. Currently, I cannot do this because if I write this whole equation, what that means is I do y1 is es over nt. And let me write h. H is h11, h12, h21, h22. Right, so I have h11 multiplied by c1 plus h12 multiplied by c2 plus n1, and I have y1 is es over nt, h21 multiplied by c1 plus h22 multiplied by c2. Right? If I want to use this one to decode this one, the problem is actually I'm corrupted by this interference, by C2. C2 creates interference to C1. If I want to use this to decode C2, well, C1 acts as interference to C2, right? So that's the reason why we have to use a joint maximum likelihood decoder. I have both observation, and from both observation, I want to decode C1 and C2 jointly. Right? But this leads to a complexity of m squared. What if now I want to do some simpler linear processing here, G, such that my observation after G, which will be Z1 and then Z2, right? So this would be, let's say, a 2 by 2 matrix. After this, I actually have only C1 on one side and C2 on the other side. I don't see the interference from C2 and the interference from C1, right? Here and there, right? Can I do that? Is there a way I can do that? Yes. Imagine, let's say H is full rank. Let's imagine that the rank of H is equal to 2, right? So what can I do? I can say Z1, Z2. I can simply say H minus 1, H1, H2, right? What will that mean? That means that we're going to have ES over NT. H minus 1 multiplied by H, C1, C2, plus H minus 1, N1, N2. Right, that's cool, because now I have Z1, Z2. What is this here? This is an identity matrix. I'm going to have ES over NT. So, sorry, NT is equal to 2. So let me write 2. ES over 2, ES over 2, multiplied by C1, multiplied by C2, plus N1 tilde, N2 tilde, right? And the N1 tilde and N2 tilde is from H, the inverse of H multiplied by N1 and N2, right? Okay, so now it's cool. C1 does not see interference from C2, C2 does not see interference from C1. Now I can use a SISO decoder here, ML and ML there. I will have a complexity here that scales with M, the number of elements in this constellation, and here with M. So I will have something that scales linearly with M instead of increasing quadratically with M. Right. Okay, so this is essentially a zero forcing receiver. I'm inversing the channel matrix. I'm inversing H, right, such that I force any interference to 0. I don't have any interference from C2, I don't have interference from C1. Here I had interference from C2, here I had interference from C1. I'm doing a combiner here that force any interference to be equal to 0. And this is actually by simply doing an inverse of this channel matrix. Now this is okay when the rank is equal to 2. I have 2 receive antennas, 2 transmit antennas. In general, if you have NR that is larger than NT, if you have NR that is larger than NT, what you can do, you can still inverse the channel, and to inverse the channels, you do pseudo inverse. The pseudo inverse is given by this. For those who are familiar, it has a specific property. But essentially, this is a generalized version of an inverse. And if H, so what you do here, if I write this here in different color. So what we had this, we were doing, right, let me take one more. Right, so we were doing that, H minus 1, right? Now the pseudo inverse here, you have H Hermitian H. So you have H Hermitian H minus 1, and then you have H Hermitian, right? So this is your G, this is your combiner, right? This is my G, my combiner, right? So if I apply this to my received signals, I have ES over NT, H multiplied by C1 all the way to CNT here, plus my noise, and this is my receive observation. Now I have G multiplied by Y. I'm gonna have ES over NT, right, of H Hermitian, H minus 1, H Hermitian. I take this and I multiply on both sides. Multiply by H, C1 all the way to CNT, plus G multiplied by the noise, right? So you see that actually now H is NR times NT, right? NR is larger or equal to NT, and I transmit NT streams, right? So I have this here, H Hermitian H will be NT by NT, right? And assuming that actually this is full rank, then you can take the inverse here. And this one will cancel this one. And so effectively you're going to have an identity matrix here. And again, your observation Z, you're going to have C1 will be completely decoupled from C2, C3, C4, all the way to CNT. And you're going to have a noise here that is being now affected by this pseudo inverse that you have applied. Okay, so this is what we have here. It's called pseudo inverse. It has a certain property, and I will show you actually what the pseudo inverse does in a minute. But essentially, it's tried to force the interference to 0. That's the first condition, forcing any interference to 0. So you want to make sure that after applying your linear combiner here, what you end up with is your NT symbols actually completely decoupled from each other. They do not create interference from each other. Okay, good. So now what is the drawback of doing that? Well, you can see it here, right? You have that here, right? So you have H minus 1 multiplied by the noise, right? So that means that now the power of the noise will actually be related to your channel matrix here. And so what's happening is that if some of those singular values of this channel matrix are small, because of the -1, you have something that is small, no to the power -1 is 1 over something small, is actually create an amplification. So the effect of this is that you actually have an amplification of the noise. If you have a channel matrix that is not well conditioned, you can still inverse it, it's fine. But if you have a 2x2 matrix here and you take this as VD and one of the singular value is much larger than the other one, the rank can still be equal to 2, but one of them will be quite weak. When you do the inverse, essentially you will amplify it, and you will amplify that noise. And so that's called noise amplification. It's very, very common when you do zero forcing equalizers. So zero forcing receiver here in MIMO, but this is actually the same principle as a zero forcing equalizer. If you have seen or heard about equalization, when you have frequency selective channels and you have interference between symbols, you can do a zero forcing equalizer. It works exactly in the same way as what we have here. You have the interference between symbols, you can do it here in a way. C2 creates interference to C1, and you want to equalize it such that you want to get rid of the interference that C2 creates to C1. And so zero forcing equalizer is one of them, or zero forcing receiver is one of them. And that creates noise enhancement. So let's see that. So where's my noise enhancement? Well, let's look at the covariance matrix of the noise. So that's G multiplied by N, right? So if I do that and I compute this quantity, you can easily do this at home. You end up with the pseudo inverse multiplied by this Hermitian, and this essentially is a function of this Hermitian matrix to the power -1, right? So again, that means that the power, that's the covariance matrix. So the power of the noise is the diagonal entries of that matrix, the diagonal matrix of that covariance matrix, right? And because of the -1 here, if you have some of those entries, if those eigenvalues here are small, the noise can be actually quite big, right? And this is what you see here. If you compute your SNR after doing the filter, you end up with, because you have a -1 here, the power of the noise, right? So the diagonal entries of this matrix will be the power. So if you look at the diagonal entries of this matrix, that's QQ, right? That's the power of the noise, right? And so that's why it appears at the denominator of the SNR. If those quantities are small, then your noise becomes very large. And this is something that can really happen if the eigenvalues of this matrix here, some of eigenvalues are small, right? Because if you do H Hermitian H and you do eigenvalue decomposition, something like this, right? If you do a -1, H Hermitian H -1, right? You're going to get lambda -1, the inverse of the diagonal entries. If some of those here are small, then the inverse will be large, and you will amplify the noise quite significantly, right? So that's the noise enhancement problem. So that works well if your channel is well conditioned, you have good rank, and the eigenvalues of this matrix here are more or less the same, is all right. But if you have a large disparity of eigenvalues, you can have this noise amplification that leads to performance loss. Okay, so we can compute the diversity gain if you do that. We're not going to all the math, but you can show that if you have IID channels, then the SINR here is actually has something that is chi-square distributed with a certain number of degrees of freedom, right? And R minus NT plus 1. And so you get a diversity gain that is now NR minus NT plus 1. So remember what we had with John decoding here. We had NR, right? Diversity gain NR. What do we have now with zero forcing receiver? NR minus NT plus 1. Okay, that's very different, right? So let me try to show you where that comes from. Right, let me show you where that. I want to give you some insight. Instead of going into all the math, I want to give you some insight into what's happening. So let me write this differently. So you have NR minus NT plus 1. This is NR minus NT minus 1. Right. So you have, let's say, 2 receive antennas, and you have 2 transmit antennas. When you had ML, diversity gain was NR, was equal to 2. Zero forcing, diversity gain is 2 minus 2 plus 1 is equal to 1. So I have lost 1, right? Where does that come from? Well, imagine when I say I have NT antennas, here the assumption is that it will transmit one stream here and one stream there, right? So when I do zero forcing, right, what I do effectively, I add my receiver. When I want to decode C1, right, I want to force interference from C2 to be 0. So effectively, I have 2 receive antennas. I will use one effective antenna, the receiver, to cancel the interference from C2. And what I will have left is only one receive antenna to decode C1. So I get a diversity gain of 1. If I have NR minus NT minus 1, if I have NT antennas and NR receive antennas, if I want to decode C1, C1 will see interference here from NT-1 streams. So when I want to decode C1, I will see interference from NT-1 streams. So how many effective antennas I have at the receiver, that will be really helpful to me. I will use NT-1 receive antenna to cancel those NT-1 streams. And what I would have left, the difference, is what will be very helpful to me to increase my diversity gain. This is the intuition behind it, right? So effectively, it means that because you have multiple streams you transmit in parallel, effectively you use some of those receive antennas to cancel the interference coming from those other streams. And this leads to the fact that now you have only a certain number of remaining antennas left that you can use for to increase the diversity gain. Okay, so here NR zero forcing, it's important that the number of receive antennas is actually larger than the number of streams that you transmit. Right? If you have 2 streams, in order to really get rid of the interference, you need to have at least 2 receive antennas. If you have 3 receive antennas, is better because then you can have a higher diversity gain, right? But you need to have at least the number of receive antennas has to be larger than the number of streams that is transmitted, right? So if you have 1 stream per antennas and you have NT streams, you need to have NR receive antennas to be larger than NT. Okay, a big gap. Now, if you have large dimensional system, right? If you have NR is equal to 5 and NT is equal to 5, you have NT, you have 5 transmit antennas. ML will achieve a diversity gain of 5, and here you would still achieve a diversity gain of 1, right? So it's a quite significant gap, right? What would be the total diversity gain you could get if you didn't use spatial multiplexing would be the product of those two, could be 25. Right, that's the maximum diversity gain that you could get. Now, obviously, you're still very far from the 25, the maximum one. Okay, so let me not go into the math, but I want to show you what. So this is my ergodic rate. If I do zero forcing receiver, I transmit NT independent streams. Right, so I still have the same as before. I transmit NT independent streams. So I have NT, and I have NR. And so I have 1 streams, 2 streams. They're all independent from each other. So I still have spatial multiplexing, right? They're all independent from each other. I can achieve now multiplexing gain, right? This is still the minimum of NT and NR. So this is the same as what I can get with the ML. And actually, I did not mention the ML here because we discussed this already before. Yes. If you look at the multiplexing gain that is achieved by ML is also a minimum between NT and NR. So the same is actually maintained here with the zero forcing. You can still transmit a minimum of NT and NR. The prelock factor of the rate will be the minimum of NT and NR. Right, so that does not change. But you don't achieve really the capacity because this term here is actually smaller than the terms you could have if you look at the capacity. I will not go into all those details. So that's just the main idea. Right, so let me explain you this zero forcing because you're going to play with zero forcing quite a bit in MMSC quite a bit. But let me explain it differently. Instead of doing the inversion, let's look at this in terms of doing an SVD and trying to find some precoding matrix that falls into some null space. So let's try to see that. Okay, so what the zero forcing combiner does, or the zero forcing receiver, when I was doing the pseudo inverse, what we try to do is to maximize the SNR under the constraint that the interference from all other layers or streams, the same thing, are nulled out. Right? So important bit with zero forcing, you want to make sure that any interference from the other streams are completely forced to 0. That's completely nulled out, right? But if you have nr is larger than nt, you have some degrees of freedom, right? If nr is equal to nt, you can just do an inverse. But if you have nr larger than nt, you have some degrees of freedom, right? And so you can use those degrees of freedom to null out the interference, but additionally to maximize the SNR. Right. Okay, so what does that mean concretely? Is that imagine you want to decode the stream Q, right? And so you want to design a combiner for that stream Q, right? And what you do is that you project the output vector onto the direction that is the closest to the column of H that is corresponding to the stream Q, but still that is orthogonal to the space that is spanned by the other vectors, the other columns of that matrix, right? So let me write this. H is H1 all the way to HNT. Okay, so I have here H multiplied by C is essentially H1 C1 plus H2 C2 plus all the way HNT CNT. Okay, I can have the scaling factor 1 over square root of NT if you like, but that does not change anything. Right, so this is what we have here, but now I want to stress specifically my stream Q, right? So when I want to decode stream Q, I now have the interference from NT-1 streams here, right? Okay, so what can I do? What I want to do, I want to find a combiner. So I want to multiply here by a GQ Y, so that I have GQ, HQ, CQ, plus GQ multiplied by this sum, plus GQ N. I want to find a GQ so that GQ multiplied by this sum is equal to 0. I want to design GQ, the combiner here for stream Q, so that I force the interference to 0. This term has to be gone, right? Important thing. And once I've done this, so that means actually GQ will have to be orthogonal to the space spanned by all those columns. GQ gonna have to be orthogonal to the space spanned by all those HP with P different than Q. Okay, GQ has to be orthogonal to the space spanned by all those HP different than Q. And being orthogonal to that, I want to find the GQ that will be the closest, that will be matching HQ. So that will be the closest to HQ. So to do some kind of maximum ratio transmission in the direction of HQ while still being orthogonal to all those HP. Okay, so how can we do that? Well, you can build a matrix H minus Q, which is H, but where I remove the column HQ. So I take all those columns P, but with P different than Q. Okay, and then I do SVD. Good. Now let me give you an example right away so that you understand that. Okay, so let's say I have C1, C2, I have 2 transmit antenna, and I have 3 receive antennas. Okay. Now let me take something a bit more complicated. I have 2 and 4. Right, that looks good. So I have 3 and 4. So I have right. So I have C1, C2, C3, 3 antennas, and I have 4 receive antennas. Right. So I have H. So H is NR by NT. And R by NT is 4 by 3. Okay. Let's imagine my Q is 1. Right. So I can H minus 1. Right, following this, I want to decode C1, right? That's the one I'm interested in, right? So H minus 1 will be, H is H1, H2, and H3. is H2 and H3. What's the dimension of this? 4 by 2. Okay, I have 4 by 2 matrix here. And I can do an SVD, right? I can do an SVD. So if I have 4 by 2, I can write a matrix here. That will be a 4 by 4. I can write a matrix here. That will be a 4 by 2. And I can write a matrix here. That will be a 2 by 2. Okay? Right singular vector, left singular vector, singular values. Right? Now here, I'm going to have singular values that will be 0. That's a 0 matrix. And here I have 2 singular values, non-zero, right? Because I have a 4 by 2 matrix, so I have at most two non-zero singular values. But this block is 0. This block is a 2 by 2 corresponding to this block. So this is what I call U tilde here. And this one is U tilde and U dashed. Right? So what do I have here? I have here something. Those left singular vector correspond to those 0 singular values. Right? So what I want to do, I want to design a combiner here at the receiver. I want to design a combiner at my receiver so that if I multiply on the left side here, sorry, this one here, if I multiply G here on the left side, I will be orthogonal to that, right? So how can I do that, right? If I use G falls into U tilde, if G falls into U tilde, automatically I'm going to have G multiplied by H minus 1 will be equal to 0 because G will fall into here, will excite those non-zero block here, and so I will have 0 coming out, right? This is the idea. I first multiply by this U tilde Hermitian, right? If I multiply by U tilde Hermitian, then you have here, you have U tilde Hermitian, right? Multiply by this, you have UV, U tilde. You're going to have this and 0, and this is non-zero, right? So this will be aligned to this. This will be orthogonal to that, right? So if you have that, once you do the calculation, because this will fall into this and will be orthogonal to that, this whole term here will be equal to 0. I'm going to have a 0 matrix, right? So what's going to happen here, if you express the whole thing, you have U tilde Y. Your Y is here is HQCQ plus your sum. That's nothing has changed. The sum and HQCQ multiplied by now your U tilde, right? Now, because your U tilde H minus 1 is equal to 0, right? You actually excite this non-zero block here. You end up with this guy is equal to 0. Right? You actually find the you find the GQ that is orthogonal to those column H2 and H3. So if G1, I could call G1 is orthogonal to H1 and H3, that means actually G1 multiplied by H2 will be equal to 0. G1 multiplied by H3 will be equal to 0, simply. Okay, so I'm gone here. So I don't see any interference from those streams C2 and C3 here, right, by doing that. So now I have U tilde H multiplied by Y will be equal now to H1 C1 plus U tilde H multiplied by N, right? C2 and C3 are gone. Good, so what should I do after that? Well, this was a dimension, this is 2 by 4, right? So this is a 4 by 1, right? Right, that's sorry, that's a 2 by 4, not 2 by 4, 4 by 2. Right, this is 4 by 2. 4 by 2. Now with the H Hermitian is 2 by 4, right? So this means, let me add one more slide. Right. So now I have a vector here. Let me call this Z. That is H1C1 plus some noise. Right. What is the dimension of Z? 2 by 4 multiplied by 4 by 1 is 2 by 1. And I have here U tilde H, obviously. Right. 2 by 4 multiplied by 4 by 1, this is 2 by 1. Okay, so now I have 2 receive antennas, and I have only 1 streams, and I have noise. What would be that noise? That would still be AWGN noise, because this actually comes from a unitary matrix, right? So the noise here will still be AWGN. So I have 2 by 1, and now what can I do at the receiver? I do maximum ratio combining. So I can do MRC, and if you do MRC, what you do is you combine with your channels. Your effective channel is here. So what you do at the receiver, this is your effective channel, H effective. You do H effective Hermitian multiplied by Z is H effective multiplied by H effective C1 plus H effective H multiplied by the noise. Right. This is Z prime. This is a scalar 1 by 1. Okay. And now this is your whole your whole channels here will be H1 Hermitian. I take the Hermitian of this multiplied by U tilde, the Hermitian of this, multiplied by HE is U tilde Hermitian multiplied by H1. Right. What is my combiner for G1? Effectively is this. This is my combiner G1. Okay. So what I have done here, and this is the expression you have here for your combiner for stream Q, is first you design here a combiner such that you make sure that you force the interference to 0. So you actually, after projecting along U tilde Hermitian, you actually have created 0 interference. And once you have that, you still have a certain number of effective antennas left. In this example, I have a 2-dimensional vector left. So effectively, I have 2 antennas left, right? And those 2 antennas left, I combine them in order to maximize the SNR after combining. And how do I do that? Maximum ratio combining. Okay, so that's the idea. So now this expression, you can show that this expression is actually equivalent to the one we had here. So to the pseudo-inverse. The pseudo-inverse does that. It actually forces the interference to 0, but while doing this, it tries to maximize the signal strength while forcing the interference to 0. Right? So those two expressions are equivalent. There is a bit more lengthy to show that, but it gives you exactly the same results. Okay, so this is actually something that is quite reminiscent of what we did with the MMSC receiver. If you remember, in the MMSC, what we did was we first whitened the noise, and then after whitening the noise, we were actually maximizing the signal strength, the SNR, right? Here is a bit similar. We force the interference to 0, and then we maximize the SNR, right? So the kind of 2-step procedure that are quite similar to each other. It's not exactly the same, because when you force the interference to 0, you actually don't care about the noise power. You just want to get rid of the interference. And so what can happen is that if the interference is actually not that significant, but you still force the interference to 0, this can actually not be a very good idea, because if the interference is not that strong compared to the noise, you better take into account the noise rather than actually really trying to force the interference to 0, right? So in the MMSC, what we were doing, and I will come back to this, we were seeing this as actually some form of colored noise, AWGN plus some interference here, and we were trying to whiten this, right? So by doing this, we don't only take into account the interference term, we also take into account the noise. This is what we're gonna come back to MMSC next lecture. Okay, so here we don't do that. We don't care about the noise here. First, we just want to get rid of this interference. So that's why I'm projecting along your tilt here. Get rid of the interference. And once I have that, then I want to maximize the SNR, and that's why I'm doing the maximum ratio combining. Okay, so let's stop here for today. And what we're going to do on Thursday, we're going to look at the MMSE receiver and then successive interference cancellation. And then we're going to compare those different type of receivers and see how much performance gain we can expect from one and the others. But this is something you will play with in your coursework too. You will have MIMO systems, and you're going to have to implement different receivers and see the error probability with different receivers. Good. Thanks a lot. And again, if you have questions, be in touch, either with me or the GTAs. And otherwise, that's it. Have a nice week. Bye-bye.
Thank you, Professor.